structures and materials. Ladies and gentlemen, in this lecture we will talk about uncertainties in analysis and design. Many of the discussions and some of the important aspects on uncertainties in this lecture are actually proposed and discussed and presented and experienced by Dr. Hariharan, who has been formerly with Engineers India Limited. Therefore, we pass on the credits to some of the points what we discussed in this lecture to Dr. Hariharan. In this lecture we will primarily have our focus on steel piled jacket structures and their top sides. Essentially in India, practically all structures being designed and constructed in our country are of this type. Therefore, we will focus uncertainties specifically applied to this kind of structure. If you look at the design process, there are many stages and steps involved in a design process. Let us see what are the stages one by one. In step number 1, let us say we are going to start the design process. First, we have got to understand what is the functionality of the platform which we are going to design. The functional aspects is first looked at. Then once you understand the functional aspects, then you talk about what are the requirements of the top side, how the layout is going to be playing an important role in the design, and what are the different kinds of weights which are going to act on the top side. Then of course we also focus on at what water depth the structure will be located, what will be the geotechnical data of that site, and what will be the storm data at that specific site. Therefore, we also will be bothered about what would be the spread restrictions in terms of the platform installation, how far and how radially I can go spreading the platform installation in a given site. This is very important because then our geotechnical investigation should essentially focus on the entire area or the spread restrictions of this area where the platform is supposed to be installed, which is to be all considered in the design stage itself, because this is what we call as the starting stage of the design. Of course, we also look closely at the restrictions, if any, in the fabrication yard. You have been understanding in the lectures of this module that how a jacket structure which a template type model is actually constructed in the fabrication yard, then launched or loaded out to the sea. So therefore, if any restrictions are there in the fabrication yard, one must look at those restrictions and take care of these restrictions in the design stage itself in the beginning. Of course, we should look into clearly the load out options and the transportation requirements of the overall jacket and the members in the top side in detail and the deck mating before we plan for such design in the initial stage itself. If we have any geometric restrictions in terms of operational point of view, for example, if your barge or if your crane availability or if your sea state weather conditions etc. are demanding a specific geometric restriction of your design, then you must look into that restriction in the starting stage of the design itself. Having understood this, in the step 2, that is the second stage of design process, we focus on the configuration of the platform. We of course determine and design the structural configuration and the framing arrangement totally based on the above parameters what we discussed in the last slide. We can use a simple spreadsheet calculation to get the overall parameters assigned in one shot, and let us try to fix up the structural configuration of the platform considering all the above parameters what we discussed in step number 1. After understanding the geometric layout and the structural parameters, we must now decide on what would be the diameter of the pile, how many numbers of pile will be there, and what would be the penetration depth. Ladies and gentlemen, we clearly understand that the geotechnical investigation plays a very important role in fixing up these 3 parameters closely associated to the piling. Then of course, based on this we work out preliminary member sizes of the platform. In step number 3, we proceed with the analysis and design. You will now understand, to perform an analysis and then carry out the design, essentially we require the basic objective dimensions of the members, what we call as preliminary sizing. Preliminary sizing is done in step number 2 much before we start actually doing the analysis. So in step number 3, we do different levels of analysis. The first level what we call is in service analysis. There we focus at the extreme and operating storm conditions, the seismic excitation in the specific area where the platform will be installed, and of course we look at the fatigue estimate and the lifetime estimate of the proposed structure. So at the end of this lecture I will discuss the equations associated with the estimate of fatigue life and the lifetime of the structure. We also, followed by the in service analysis, we also do what we call pre-service analysis. Before actually you put the platform in service, the platform should sustain the loads arising from or during fabrication, during the installation process like load out and transportation, and launching, lifting and appending, because these are different stages where the platform will be subjected to erection and installation stresses on different members, which can become critical and the platform can fail during any of these stages of operation as well. We also look at the on bottom stability of the platform and the mud mat design, which we call as pre-service analysis. Once the pre-service and in-service analysis is complete, then we look for the field engineering aspects of uncertainties. The foremost aspect in field engineering problem is material availability. Normally if the suggested member size is not available, one must always opt for an higher size of the member instead of compromising the size, quality and thickness of the member. That is the standard thumb rule adopted in the field engineering practice, that if the available or recommended size of the design is not available, always opt for the next available higher size of the member, because this will lead to a conservative design. The smaller members with of course local reinforcements can also be suggested sometimes to meet the requirements in case if the immediate higher size member is not also available. There are specific site problems and issues related to field engineering associations, they all should be addressed in advance. If we look at the analysis procedures, then uncertainties in estimation of environmental forces on structures plays also a very major role. We are using regular wave theories, we of course use wave current interaction in the analysis. We also talk about extension of this to still water surface to the member depth, the Morrison equation and extending the Morrison equation to 3-dimensional studies, and of course a big arbitration going on in the values of drag and inertia coefficient which are used in the Morrison type forces, because Morrison type forces always take care of the CD and CM values, and CD and CM values depends on variety of parameters and they keep on varying along with the water depth and member dimensions and site specific. Therefore there are very high class of uncertainties associated with these of the factors which are all inherited in the analysis procedures itself. Of course one follows stiffness method of analysis, which is considered to be reasonably accurate from the past experience of analysis and design. Uncertainties in estimation of local member stresses mainly due to joint flexibility is a very important lacuna if you do not take care of this practically in a proper manner. Of course there are no major uncertainties in member force estimation, which essentially comes from stiffness method of analysis. Therefore stiffness method of analysis is considered to be one of the advanced and better technique for analyzing offshore jacket structures in detail. Having analyzed the members, then we talk about the design procedures. The main design work in any given offshore structural design is actually not designing the member sizes, but checking the existing member sizes for its adequacy to carry forces or combination of lower forces. We will do some examples in the next lecture to make you to understand how to estimate the existing member level criteria for different combination of forces from recommended by international codes like ABS and API. We will do couple of numericals to make you to understand how these are actually done. So the main design work, ladies and gentlemen, is focused on not arriving at the sizes, but checking the existing member dimensions for the forces coming on the member or for the combination of forces acting on the member. This is what we call as adequacy check, and these are actually defined by several standards and international codes which can be followed for different combination of forces coming on offshore structures. The member adequacy checks as recommended by these international standards and codes are reasonably accurate, they have very little degree of uncertainty and they have been practiced very widely all over the world, and structures do exist degree of higher safety when these are followed from these international codes. Therefore, we can confidently say or make the statement that the level of uncertainty associated with the adequacy checks proposed by standards and international codes are very limited. Joint adequacy checks are again based on the empirical formulae which are derived from the model tests as determined by specifications. These have been updated several times based on the more research and analysis, and you can find them in the empirical equations in these codes as well. For example, if you look American Petroleum Institute recommended practice 2A, which is following working stress design, which is one of the primary standards for design of offshore structures and jacket structures, owner specification could become more stringent, which can be much more higher in terms of its classifications with respect to this code. This code recommendations are the basic minimum requirements which one must follow. Of course, the owner's engineer's recommendation and suggestions can be even become more stringent than what the code says. Having understood that we will obtain and check the member sizes and dimensions from the API or ABS codes, then we talk about different size of members in the structure which are governed by load conditions and different load combinations. Such members will be generally safe for other loading cases. Substantial number of members are required only for taking care of pre-service conditions. Many member sizes are generally governed by KL by R limits consideration or D by T, that is diameter by thickness limitations in the international codes. Therefore, uncertainties in design will primarily arise on account of uncertainties from the design codes itself, which arise essentially from inadequacy in background research information. Therefore, ladies and gentlemen, it is very vital and important as an offshore engineer that we do conduct lot of model investigations, experimental studies to update the characterization of the member quality and the member sizes and member characteristics, which can get followed up and printed on these international codes for the benefit of offshore engineers in practice. So, APRP2A for example has undergone 21 revisions in about 30 years of span of time. So, you can understand that how stringent regulations have been proposed by these kind of international codes, which can be followed by the professional engineers for designing offshore structures in site. Some of these decisions and revisions had minor impact of course on the design, some of course had very major impact on the design formulas. If we look at the seismic analysis, which is also becoming a growing concern in offshore structures which are located in near fault areas, or at least checking the adequacy of these members or the members of the structures in near fault area, it is better that we generally use full response spectrum magnitude for the design. You design the double value for rare intense earthquakes. Generally the wave forces are seen to be much higher than the seismic forces. Only deck legs which are normally braced are critical in seismic condition. This has been evidently seen in many of the design practices what we have done in case of offshore structures. Uncertainty in member force evaluation essentially comes from the following factors, because it is subjected to random vibration, it is subjected to multi-directional excitation, that is 3 directions, principal direction excitation can happen from the seismic forces, combining the responses from different modes, and limitations are like square root of sum of squares, CQC rules, etc. So, these modal combination rules can impose certain level of uncertainties in the member force evaluation when you do actually analysis for seismic forces. Most importantly, when we talk about offshore structures, since structures are subjected to reversal of forces and stresses throughout the lifetime, fatigue analysis plays a very important role, and let us quickly see what are uncertainties associated with the fatigue analysis. Stress concentration factors plays a very important role, because these SCFs are essentially arrived based on empirical formulae given in the codes. We are talking about multiplanar joints, which is also one of the important source of uncertainty for fatigue analysis. Of course, we can use SN curves and Palmgren-Menner linear cumulative damage hypothesis, which has got limitations. We will discuss about this hypothesis now at the end of this lecture. The major question comes if I say what do we understand by damage equal to 1, how do we interpret this in my fatigue analysis. It is a very important uncertainty which is still to be answered. Of course, we talk about crack initiation and propagation, where we are going to talk about the fracture mechanics. Fracture mechanics algorithms also have limitations in its applications for different kinds of reversal of stress combinations. Of course, we have a very serious saving grace in fatigue analysis. Let us see what is that. Of course, 90% of the joints have fatigue life in excess of 1000 years. This has been seen by practical assessments done on members in offshore structures. Actual critical joints will be only about 10 to 20, with computed fatigue life lesser than 100 years. These are the joints which one must evaluate very carefully when we do fatigue analysis for members. So, it is very easy to increase the fatigue life at minimum cost added to the structure. SN curve, of course, which is being followed commonly, is a conservative estimate of N2 cycles. There is a substantial reserve available if you follow this procedure in your analysis. Factor of safety in the computed life is very important aspect which is taken care of as an important grace in fatigue analysis. Periodic underwater inspection, ladies and gentlemen, is a very important task which people have now realized and getting followed, because this can help us to assess the existing service conditions of the critical joints. Arresting crack propagation, underwater wet welding just below the water level in case of cracks are repair methodologies which are now available, which can improve the service life of the structures much before they get into unrepairable sequence of damage levels. Let us talk about reliability. How reliable is my process of design and analysis? What are uncertainties? How reliable are the present analysis and design procedures? Because it is a very interesting question asked by any offshore designer, just to understand how reliable am I doing my analysis and design. When in doubt, always understand that remain conservative in your analysis and design. APRP 2A exclusively has a chapter 17 which talks about assessment of existing platforms, which gives lot of recommendations and suggestions for doing reliability study on offshore structures. We can always do what we call design level analysis or a pushover analysis to exactly find the reserve strength ratio of the existing structure. An existing platform is accepted only if it is found safe for less than the current loading. Remember that no excessive loading at any point of time is permitted in the design stage at all. Indicating confidence in the current design procedure has become a very important and very explicit practice now for design of offshore structures. If you talk about safety and reliability issues during construction installation stages, it is a very interesting factor. Let us see them now one by one. Let us see what are the safeguards I can do in terms of engineering perspective. The owner's engineer actually reviews and approves all engineering deliverables in terms of its design practices. The certification agency, of course, once again reviews them, and of course they do reviewing only on selected items. In added to it, the marine insurance agency for all operations also review after the land fabrication is completed. The marine warranty surveyor also reviews the whole process and approves all designs and procedures related to these operations, including the installation and construction methodologies. The installation agency again reviews and gives acceptance to all of them related to his work. Therefore, you can see in safeguard assessments in engineering perspective, there are multi-level checks being calculated and applied on offshore structures, starting from the owner's level, that certification agency, the marine insurance agency, the marine warranty surveyor agency, and the installation agency. So, at different levels a thorough execution of check has been done, including the design, analysis, construction, installation methodologies completely applied to offshore platforms. If you look at the safeguard levels in fabrication stage, interestingly extensive non-destructive tests are conducted on the members, and documentation of the fabrication checks are generally established much before the construction or the installation takes place. In this case, the owner's engineer the third party inspector and certification agency, all of them independently review and monitor the fabrication work. Ladies and gentlemen, it is very interesting and amazing for you to understand that fabrication stage safeguards are exercised with very stringent methodologies, like owner's engineer checks it once, the third party inspector also inspects the members for its fabrication checks, and of course the certification agency reviews independently, and of course he employs people to monitor the fabrication work in the yard itself. So any deviation which are seen from the approved drawings are to be reviewed thoroughly, and they are approved by the engineers and the owner subsequently before the construction installation is carried out. Installation agency, the warranty surveyor reviews all these items once again, which are relevant of course to their domain of work, and apply all possible checks thoroughly before the fabrication is cleared off for erection and installation. It is therefore expected that practically all errors, mistakes or anomalies would be captured during the fabrication stage and rectified during this review process thoroughly. If you look at the safeguards during installation time, interestingly installation engineering is reviewed by the owner's engineer, installation contractor and the warranty surveyor independently by the group of engineers. Every operation of installation is reviewed thoroughly and approved by the warranty surveyor before he adopts this practice of installation for the platform. Ladies and gentlemen, remember that commencement of any operation of installation is only approved after one has studied a 72-hour weather forecast thoroughly. If the weather forecast for 72 hours is not available, then a detailed operation of commencement is not approved by the engineer. Every operation and critical equipment has therefore a standby or a backup in order to avoid any delays due to malfunction. So notwithstanding these safeguards, mishaps generally occur which have taken place, but they are seen very rarely in offshore accident cases. Therefore one can understand proudly and say an offshore platform is one of the most thoroughly engineered and reviewed construction with very stringent norms adopted in practice. With all these stringent norms adopted in practice, still there are uncertainties existing in the fabrication stage. Primary uncertainty essentially comes from material availability. There can be non-availability of requisite material at required time in the sequence of fabrication. That is a very important part. Your material may be available, but at a specific sequence of operation that specific quantity of material of that specific grade of marine steel may not be available due to various reasons of cost factor, etc. So one is supposed and compelled to have a substitution with an equivalent or a superior material and of size and dimension. Ladies and gentlemen, is very important, though the issue is generally minor, but you have got to handle this very carefully, and of course in construction sequence and fabrication sequence these issues are handled as a routine part of the job. Inadequacies of detailing in design drawings, for example the design drawings may not have all thorough details as required by the fabrication contractor. There can be some inadequacies in certain cases generally captured in the review and they are corrected in the review process itself. Otherwise the fabricator will incorporate during preparation of the shop drawings himself, get it approved from the agency before he completes the fabrication, because critical items have to go back to the engineer and designer for review and approval must be obtained on these. So the fabrication errors captured during inspection and they are rectified thoroughly in the stage itself. If you look at the load out operation, there are uncertainties associated during this stage. The deviation from methodology proposed in the initial stage and details assumed in the strength checks are then thoroughly revised, and then a revised analysis is computed to ensure the structural adequacy during load out operation. Equipment failure during transfer to the barge with rising or falling tides, which are of course rare, will always have a backup to safety. Certain of these potential scenarios are analyzed for certain structural adequacy during engineering stage itself by the designers. If you look at the transportation segment of uncertainties, then one can talk about there can be a prevalence of rough weather or cyclone during the transportation stage. the barge plus the structural system should be analyzed for such rough weather combination likely to occur during the installation stage. There can be a possibility that the maximum sea state expected during transit through the various sea seasons and locations should be examined thoroughly and reviewed. There can be a possibility of damage which can occur to the barge. The barge should be inspected and certified for what we call seaworthiness. Further inspection should be done before mobilizing the barge for transportation of the platform. There can be a possibility that the damage can occur during transportation because of collision. One should take care of safe operation during collision and of course during grounding as well. During installation, once the loadout is complete and transportation is there, in the site underwater or offshore there can be a possibility again because of rough weather or cyclone. You have to wait and watch for the weather improvement when you do installation offshore. The launching or let us say the sinking of the jacket after launch is an important failure of buoyancy element. This can be controlled by checking the damaged compartment scenario, which is a part of the routine design generally done for offshore structures. Unpiled stability of the jacket and mud mat design can also result in jacket toppling during installation, particularly it is having a high potential in case of soft soil locations. Less serious of course jacket tilting during installation. This can be handled by jacket lifting and rectification during piling. It is one of the standard feature which generally comes across in all the construction scenarios of jacket platforms. There can be problems associated with the sloping seabed, generally captured during the surveys, and it is taken care of the design. We do generally what we call stepped mud mats. There can be uncertainties continuing installation as you see here, essentially coming from pile driving. The drivability may result in what we call premature refusal depending upon the soil stratum. There can be an improper hammer performance. The accuracy of soil information cannot be available to the designer in the beginning. There can be extensive variability of soil parameters and the subsea strata. There can be a possibility of overdriving the pile. One higher size hammer is normally mobilized so that this problem can be taken care of. There can be a remedial equipment which can be taken as a standby during the pile driving operation. You must accept without remedial action based on back calculation of the capacity of the pile. Accept with reduced factor of safety because remedial action is not possible for any such reasons applicable during installation. There can be problems associated and uncertainties coming from installation during the grouting stage. There can be inadequacy of the grout strength which are detected from the tests conducted in situ. Then in that case use a conservative design to cater to this scenario. Remedial action because they are very expensive, not normally carried out. Generally the conservative design is carried out for grout inadequacy in the design stage itself. Grouting can also have problems associated with shear keys which are not available in the sleeves due to underdrive. In such cases increased grout strength with special mixtures can help to counteract this kind of problems. There are specific uncertainties associated with topside installation. Let us see what are they. The major problem arises in lifting. If the design does not match the lifting arrangement or if detailing is inadequate to properly transfer lifting loads, then the balance of structure will be disturbed. Generally these kind of errors are captured in the review stage itself. Great attention is paid to these kind of aspect in the design stage itself. There can be a problem associated to sling length tolerances. No impact in statically determined structures lifts because there are no such difficulties arising from these problems. Of course there can be a skew distribution if a structure is indeterminate because of this kind of lifting operation. This is one of the routine design factor which generally checked in the design stage itself. Of course there are very serious human factors which can contribute to high level of uncertainties. Human errors are considered and seen as one of the major cause for many accidents and mishaps in the recent past. This can be arising because of inadequate knowledge of construction engineering, inadequate training and experience imparted to the engineer. It can be also arising from the lack of application of the knowledge at the time when they are in demand, there can be serious non conformance to safety practices advised by the warranty surveyors, etc. So, there are many aspects where we have seen that these plays important role in carrying a safe installation operation. We will now discuss how to calculate the lifetime estimate of the offshore structure and what would be the uncertainty associated with this kind of problem in the blackboard. So, as we said in the lecture, there can be uncertainties associated with the fatigue damage. Let us quickly see how to estimate the lifetime of a service life of a structure based on fatigue damage. If I have a material which is essentially metallic, is subjected to magnitude of stress which exceeds the threshold value of the material, then ladies and gentlemen, interestingly there exists a connection between the stress exceedance and the number of times of this exceedance. The stress exceedance is actually related to the value of stress compared with the permissible or threshold value what you recommend in the design, and how many times in a given service life or in the given stage this level exceedance occur, that is also very important, what we call the cycle of exceedance. So, therefore, the connection between the stress level and number of stress cycles which is required to fracture the material is given by a relationship we call this equation number 1, where in this equation m and k are actually material constants. Usually the value of m is equal to 3 to 5. N denotes the number of stress cycles leading to fracture, and of course S denotes the stress range which you are considering in your calculation. There is a very common hypothesis applied to estimate the fatigue damage which we call Palmgren-Munoz rule. So, according to this rule, for a low time history of t, with different stress amplitudes, the cumulative damage caused by fatigue is given by d tilde of t, which is summation of j of Nj by capital Nj, equation number 2, where Nj is the number of stress cycles associated with the stress range. So, you will fix up a stress range, and what would be the number of stress cycles associated with that stress range is what we call as Nj. Now, the stress range can be Sj minus delta S by 2 to Sj plus delta S by 2. So, half of minus and half of plus, where delta S is what we call discretion length of this. And capital Nj will be given with the first equation, which we can say k Sj to the power of minus m. We already know k and m are material constants, and S is of course the stress range for the jth cycle. Now, fracture is occurred when d tilde t becomes unity. When both of them are same, then we can say that fracture has occurred. Having said this, let us see how I can relate my cumulative fatigue damage estimate to the life estimate or service life of the structure. Essentially, the damage occurred or accumulated using this model is linear. That can be one of the limitations of this application. Let us say for example, let us x of t be a random process which is stationary and narrow band that represent the von Mises stresses in a section of a lightly damp structure. We also assume that x of t is a zero mean process. I say n bar of A denote the number of stress cycles between this range A and A plus dA and therefore n A bar A will also be a random process, because whenever the stress value exceeds the von Mises stress exceeds the threshold value, the number of stress cycles which exceeds this value between the given range is again going to remain random, whereas in this case the stress range S can be 2A, that is S minus A to S plus A is the range, therefore we can say the stress range remains as 2A. Now the accumulated damage as given by the model d tilde of t can be now n bar A by n A dA n of A. Equation number 3. We already know n of A is given by k S inverse minus m. In my case my stress range is nothing but 2A, because I already said the stress range is 2A, which is also a random variable. Now having said this, let us calculate the expected value of the accumulated damage which is d of t, of course we know is expected value of d tilde of t. We already know d of t is given by 0 to infinity expected value of n tilde A dA by Na. Equation number 4. Now, we already know that expected value of n tilde a dA is the expected number of stress cycles with an amplitude between A and A plus dA during, of course, the time t. That is why I am saying this d of t. So, I am having a period of record which is t. So, if that is the case, I can write the expected value of this as Vx plus 0 of t Fxp A dA, where Fxpa is the relative peak number of peaks between A and A plus D. Vx plus 0 t will be the total number of peaks. Well, that is what the expected value of n of A is, and this can be equal to the number of cycles within the period t. So, based on these expressions, now I can write d of t can be t 0 to infinity Fxpa dA by n of A, which can be said as Vx 0 t. We already know this value Fxp, which is 2A to the power m. 2A is the stress range by K, that is what I am calculating this value as Na. So, Fxp of A d. Na can be estimated directly using the first equation, and this is what I am substituting. I call this equation as 6. So, we will continue this simplification, then integration of this to get the service life T or the lifetime T estimate in the next lecture.